So wherever you have Fraunhofer diffraction through a single slit, whether bright or dark, we will consider it to be bright fringes, because n is 1 first angular position 5.55 into 10 power minus 7 meter, and they have not mentioned any medium like oil or something, which means hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram Pre-University, Mysuru. What is that I have stored in my magic bag today? It is the second session of problems from the chapter Wave Optics. Hope you people have followed the first session, gone through the problems, simplified the problems, gone through the relations, and I expect you have come prepared for today's class. The first problem today, the problem says, calculate the distance between the 15th and the 25th fringe. Interesting. I'll tell you why. Calculate the distance between the 15th and the 25th fringe in an interference pattern. Analyze this statement. He is simply saying 15th and the 25th fringe. Whether it is a bright fringe or a dark fringe, it is not mentioned. Alva? Albari 15th and 25th fringe. If they are not mentioning whether bright or dark, we will consider it to be bright fringes. So I have to calculate the distance between the 15th and 25th bright fringe in an interference pattern due to two narrow slits separated by 0.25 millimeter. Andre, distance between the two slits is 0.25 millimeters, and the light of wavelength used is 600 nanometers, which is lambda. The distance between the slits and the screen is 1 meter, which is capital D. So I have to calculate the distance between 15th and 25th bright fringe, given small d is 0.25 millimeters, lambda is 600 nanometers, capital D is 1 meter. Now, let us recall the distance of a bright fringe from the central fringe. So, we will recall the distance of a bright fringe. So, a bright fringe from a central fringe. Come on, students, give me the expression. Very good. So, it says x equals n lambda d divided by small d. But what is that I am calculating according to the problem? Distance between the 15th and the 25th bright fringe, which means x equals n2 minus n1 lambda d divided by small d. So x minus x2 ಅಂತಲೂ ಬರಿಬಹುದು, which is n2 minus n1 lambda d divided by small d, or x2 minus x1 is 25 minus 15. So what is this? Distance between the 25th and the 15th bright fringe. Lambda is 600 into 10 power minus 9. D is 1 and small d is 0.25 into 10 power minus 3. So when you simplify, we nearly get it around 24 millimeters. So if I access the problem, just some concepts relevant to it, very easily I am arriving at the solutions. The next one. Now, the problem says monochromatic light. We are using monochromatic light of wavelength 5460 angstrom. Now, wavelength is in terms of angstrom. 5460 angstrom. Incident normally on a slit. This light is incident normally on a slit whose width is 0.1 millimeter. If you observe here, we don't say it is the distance between the slits. He says the width of that single slit is 0.1 millimeter, which is represented by small a. I have to find the angular positions. The angular positions of the first and the secondary minima. ಗಮನಿಸ್ಕೊಳ್ಳಿ ಅಲ್ಲಿ angular positions of the first and the secondary minima formed due to Fraunhofer diffraction. So ಮಕ್ಕಳೇ ಇಲ್ಲಿ ಈ ಪ್ರಶ್ನೆನ ಫ್ರಾನ್ಹಾಫರ್ ಡಿಫ್ರಾಕ್ಷನ್ ಮೇಲ್ ಕೇಳಿದ್ದಾರೆ. So the wavelength of light used is 5460 angstrom. It is incident normally on a slit, single slit of width 0.1 millimeter. I have to find angular positions for the first and secondary minima. So first and secondary minima formed due to Fraunhofer diffraction. So students, here the condition for the formation of what do you call minima in a Fraunhofer diffraction at a single slit, we say A sin theta n is equal to n times lambda. So this is the condition for the formation of minima in Fraunhofer diffraction pattern, where this n is 1, 2, 3, etc. ನೀವು ಗಮನಿಸಿದ್ರೆ I have to find the angular positions of first and secondary minima. First and secondary minima. So the first case, A sin theta 1 is 1 times lambda because n is 1. First angular position, or sin theta 1 is lambda by A, or approximately, since the width of the slit is very, very small, the angular position also becomes very, very small. So this is 5460 into 10 power minus 10 divided by, where he says the slit width is 0.1 into 10 power minus 3. Use your simplify, use your calculators, you will arrive at the answer. The second one, A sin theta 2 is 2 lambda now. The second case, it is the secondary angular position, which means sin theta 2 is 2 lambda by A. So wherever you have Fraunhofer diffraction through a single slit, width of the slit is very, very small. Means to say, angular position is also very, very small. Again, approximately theta 2. Now it is 2 into 5460 into 10 power minus 10. Again, 0.1 into 10 power minus 3. So many radians will be the answer. Very much reflecting that if you're familiar with the expression, simplification becomes very, very easy. The next one, students. Now it is based on limit of resolution and resolving power of light. For a microscope, ಇಲ್ಲಿ ಫಸ್ಟ್ ಏನನ್ನು ಅನಲೈಸ್ ಮಾಡಬೇಕು ಅಂದ್ರೆ ಈಸ್ ದ ಗಿವನ್ ಆಪ್ಟಿಕಲ್ ಇನ್ಸ್ಟ್ರೂಮೆಂಟ್ ಅ ಮೈಕ್ರೋಸ್ಕೋಪ್ ಆರ್ ಅ ಟೆಲಿಸ್ಕೋಪ್. ಸೊ ವೆರಿ ಕ್ಲಿಯರ್ಲಿ ಇಟ್ ಈಸ್ ಅ ಮೈಕ್ರೋಸ್ಕೋಪ್. For a microscope used to observe non-luminous objects, very, very important, non-luminous. The semi-vertical cone angle is 15 degrees. So semi-vertical cone angle theta for a microscope used to observe non-luminous objects. Very important. Find the limit of resolution and resolving power for light of wavelength 540 nanometers. ಕೊಟ್ಟಿರುವಂತ ಆಪ್ಟಿಕಲ್ ಇನ್ಸ್ಟ್ರೂಮೆಂಟ್ ಯಾವುದು? ವಿಚ್ ಈಸ್ ದಿ ಆಪ್ಟಿಕಲ್ ಇನ್ಸ್ಟ್ರೂಮೆಂಟ್ ಗಿವನ್? ಮೈಕ್ರೋಸ್ಕೋಪ್. ವಿ ಆರ್ ಯೂಸಿಂಗ್ ಇಟ್ ಟು ಅಬ್ಸರ್ವ್. ಏನನ್ನು ಅಬ್ಸರ್ವ್ ಮಾಡಬೇಕು? ನಾನ್ ಲೂಮಿನಸ್ ಆಬ್ಜೆಕ್ಟ್ಸ್. And the semi-vertical cone angle is 15 degrees. I have to calculate the limit of resolution and resolving power of light if the wavelength used is 540 nanometers. So first, I very clearly know it is a microscope which is used to observe non-luminous objects. So limit of resolution here is lambda divided by 2n sin theta. That n sin theta together is called as the numerical aperture. Separately, n is the refractive index. Theta is the cone angle. And they have not mentioned any medium like oil or something, which means n is the refractive index of air. So on substitution, this is 540 into 10 power minus 9, 2 into 1 into sine theta is 15 degrees. Again, simplify using your Clark's table. So it turns out to be 1.04 into 10 power minus 6 meters. So this is the limit of resolution. Now, once I find out limit of resolution, how will I find the resolving power? Resolving power is always reciprocal of the limit of resolution. Keep that in mind. It is always the resolving power is the reciprocal of limit of resolution. So we say RP resolving power is 1 divided by D. So when I divide or take the reciprocal, it is 95877. Please do these simplifications. Simplifications for you all. You will have to do that. And if you observe, resolving power is a number. It does not have a unit. Don't write meters or meter minus 1. Limit of resolution is meter. Resolving power doesn't have a unit. It's just a number. The next one. A microscope. Again, it is a problem which is based on microscope, is used to resolve two luminous point objects. Now, if you come to understand, it is luminous point objects. Previous case, microscope ittu, but it was non-luminous point objects. Here again microscope, but luminous point objects separated by 5.55 into 10 power minus 7 meter. What is the numerical aperture? Numerical aperture if light of wavelength 546.1 nanometer is used. Now the problem says a microscope is used to resolve two luminous point objects separated by 5.55 into 10 power minus 7 meter. So this is the limit of resolution of the microscope. I have to calculate the numerical aperture if the wavelength of light used is 546.1 nanometer. So, now it is luminous point objects. For luminous point objects, limit of resolution is given by the formula 1.22 lambda divided by 2n sin theta. Non-luminous point objects ಆದರೆ ಈ 1.22 ಬರದಿಲ್ಲ. Since it is luminous point objects, D is 1.22 lambda divided by n sin theta. Which is the numerical aperture here? N sin theta itself is called numerical aperture. So n sin theta is 1.22 nearly 540 into 10 power minus 9 divided by 2. So on simplification, n sin theta turns out to be 0.6. So in the first case, for microscope with luminous point objects, something called numerical aperture, n sin theta is 0.6. Now, what will be the numerical aperture and limit of resolution if air between the objective and the object is replaced by oil of refractive index 1.5? Now the problem says, if you replace that air medium, if we are replacing with something called as oil whose refractive index is 1.5, what will be the numerical aperture and limit of resolution? Which means now, if it is oil, so for oil, now numerical aperture, so n into 0.6, 1.5 into 0.6, which should be nearly 0.9. With this, now you have to calculate D, the new limit of resolution, D dash. Again, 1.22 into 540 into 9 divided by 0.9. So do this simplification here. So many meters will be the answer. So you have to know numerical aperture ant helidre that n sin theta together is called numerical aperture. So now oil has refractive index 1.6. See, air had 1. So 1 into sin theta, 0.6. Now 15 into 0.6, 0.9. That will be the answer. The next one. This is an assignment for you all. For a telescope, now it is a telescope, microscope alla. The diameter of the objective is 0.2 meter, small d. Diameter of the objective is given. Assuming the mean wavelength of light is 580 nanometer, find the limit of resolution and resolving power. Very simple. For a telescope, limit of resolution D is 1.22 lambda divided by diameter of the aperture. Again, the wavelength is 580 into 10 power minus 9. Diameter is 0.25. Substitute, you get limit of resolution. Again, what is resolving power? Resolving power is 1 by limit of resolution. So in both cases, either microscope or a telescope, resolving power is the reciprocal of limit of resolution. What is the diameter of the aperture required for the resolving power of 5 into 10 power 5? Again, if the resolving power is 5 into 10 power 5, calculate the diameter. So students, again we have come across beautiful problems in this session based on diffraction concepts and based on resolving power. Next session, few more problems on polarization. Until then, have a nice time. Thank you.